Thank you, and thank you to all of you for still being here. It's more than I expected. Okay, so let me just say a bit more about the precise topic and disambiguate the title a bit. By lightweight Agda, I don't mean some new sublanguage of Agda. I mean doing things with relatively little effort using the standard Agda. Also, I'd like it to be that you don't need to be trained for years in Agda to do this. Formalization, I mean taking a mathematical definition and checking it mechanically using Agda. And the aim there is that the formalization should be easy to relate to the thing that you're formalizing. If you end up with something that has a very obscure relationship to what you're formalizing, then you really haven't got very far. And finally, denotational semantics, just standard, traditional, recursively defined Scott domains, fixed points, lambda notation. I'll say more about that in a moment. The original motivation for this work was I had a denotational semantics from 1989, written by a former student of mine, and I wanted to check it. I thought it was perfectly okay. So I wanted not only to check the definitions, but also to check the proof steps in the proofs of the lemmas. So Agda seemed a good match for doing that, to do an equivalence proof in Agda, equational equivalence proof. So I thought it would just be a walk in the park to plug this denotational semantics into Agda, but it turned out to be a rather painful experience. So let me just recall, because denotational semantics is perhaps not such a hot topic these days as it used to be back in the 70s when I started. So Scott and Strachey here. Denotations are Scott domains, pointed CPOs, recursively defined without guards up to isomorphism. Denotations are always, in traditional denotational semantics, defined in ordinary lambda notation, and everything in sight is continuous. You don't need to prove anything about the continuity because application and abstraction preserve continuity, and if you start from continuous things, then you've got continuous denotations. And ender functions on domains have always these fixed points. Domain theory started with Scott's discovery of the model of the untyped lambda calculus. In fact, he was trying to prove it couldn't exist. In 1969, halfway through a series of seminars where he was developing the proof that it couldn't exist, he realized he'd managed to construct it with the bilimit construction. Other models have been put forward, and also domain theory these days includes predomains, which are unpointed domains. The recent, relatively recent book by John Reynolds also covers the same ground. There have been some formalizations of domain theory and of Scott's D-infinity model. In the 90s, Bernhard Reuss used Lego and the extended calculus of constructions to essentially implement synthetic domain theory impredicatively, and the code is no longer running as far as I know. More recently, Tom de Jong developed a major library in the type topology library for domain theory in Agda. So let's just briefly look at Reynolds' presentation of the model of the lambda calculus, denotational semantics for it, and then how it would look in the formalization. So this is copied from some slides I found online, but essentially a compact version of what's in chapter 10 of Reynolds' book. And it's pretty standard, except that normally you just use an equation between the domain D-infinity and the space of all continuous maps on D-infinity. Reynolds makes the isomorphism explicit and uses it when defining the denotations. So the isomorphism is this phi and psi, and we'll see how that's reflected in the formalization as well. So I actually tried using the type topology library, the formalization of domain theory, which is a well-documented and easy to find your way around in, but it's also quite substantial. So it took me some time to find my way around to start with. Anyway, in those modules, you have a construction, essentially the same construction that Scott had, more following the details perhaps in the Akim and Young handbook chapter. And we have this isomorphism between D infinity and this type of continuous functions from D infinity to D infinity. This is all based on directed complete posets, DCPOs, and the whole thing is there in Agda. To define the denotational semantics of the untyped lambda calculus based on this model, it's convenient to name the inverse of the isomorphism there, and also this app is going to be useful. The definitions are quite straightforward and not very long, but what's important to note here and important to remember that in this framework, a continuous function analytically is a pair, it's not a function. It's a pair consisting of an underlying function together with a proof of its continuity. And that turns out to be what is pragmatically, I mean, it's theoretically, it's very correct. It's a formalization of what Scott did. But from a pragmatic point of view, it turns out to be somewhat awkward to have to deal with. So this is based on the Tom's modules from the type topology library, and defining a semantic function, mapping lambda expressions, untyped lambda expressions to functions from ordinary functions from environments to elements of D infinity. And it involves also this lambda is continuous, which is used as a second, that's going to construct a proof term from an expression and an environment and a value, showing that that is actually a continuous lambda expression. There are two things. One is that one has had to specify a pair, which you didn't have that pair in Reynolds' presentation, in the mathematical presentation. That's already a little bit annoying. But what is a bit more annoying is that when you actually want to carry out that proof and give that proof term, well, it's about 3 pages in John Reynolds' book. It's not that deep. It's just a fair amount of calculation with limits and preservation of limits. But I haven't tried seriously, but it would take me far too long to take that proof from Reynolds' book and get Agda to accept it as a valid proof term in Agda. So for me, that's too much effort. That's not a lightweight approach. So I've been trying to find a workaround, basically. This lightweight Agda formalization is such that nothing special regarding abstract syntax. It's just context-free abstract syntax like in denotational semantics. It gets a bit trickier when we get to what I put in quotes here as domain definitions, which are not really domains. They're just ordinary Agda types and postulates. But then once one's done that, then the definition of the semantic functions is pretty straightforward. Just ordinary inductive definitions based on the abstract syntax. So the next few slides will just show how it looks, and you can see if you like it or not. And it's a bit awkward, actually, that you start off with this inductive data type for abstract syntax, which doesn't resemble at all the context-free grammars that you use in denotational semantics. I didn't show the one from John Reynolds' book, but it's one just uses a small context-free grammar in the usual style. Okay, in this data type, I'm just using functional notation for the constructors, just for simplicity. Agda's mixed fixed notation isn't quite general enough to deal nicely with precisely the lambda calculus, in that lambda is not allowed as a symbol, nor is dot, and you can't put 2 arguments next to each other without some other symbol in between them. So it wasn't a good match for doing the lambda calculus anyway. So this is the awkward bit, if you like, what we do with domain definitions. So this is how it looks in Agda, and Agda accepts this okay. We're just using a standard library module that defines inverses. And here we just say, okay, D infinity is just some type, some Agda type. We don't bother saying what kind of structure it is. We also claim that there is a bijection between the type d infinity and the ordinary Agda type of all Agda functions between d infinity and d infinity. Now, there is actually an instance of that assumption, which is the one element type, but that's not very interesting. And in any case, for more interesting examples, there wouldn't even be that one instance. So we're looking here at postulating properties which are not satisfiable. However, Agda doesn't actually complain about that, luckily, otherwise I wouldn't have got very far. This bit of magic here is giving us for free the instantiations of the inverse with the isomorphism. Not really, it's just a bijection. It's not really an isomorphism here. There's no other structure around. Okay, once one's done that, then this is how simple the semantic equations look. If you just type in the lambda expressions without the from and the to, in other words, without the isomorphism, Agda will complain and tell you that you need to put them in, and it will almost tell you which ones to put in. I really don't understand why Agda can't deal with implicit isomorphisms in this context. But anyway, it's not too much effort to put them in. So for comparison, that's John Reynolds' original equations. Okay, some of the names have changed. But up to alpha conversion, we're all happy, right? This is just a more conventional using rho instead of eta and so on. That's how it looks. You can even not only get it to type check, but you could actually check that denotations are equivalent based on that specification, just on that very simple, lightweight approach. For instance, if you want to know that if we have a subterm which is divergent, as this argument is, then if we forget about it and just throw it away, then that's equivalent to just having what's left in any case. That's how it looks if you want to put it in, and you get a proof by REFL. But that's not quite the whole story. To get a proof by REFL, you need to add a rewrite rule that removes the isomorphism pairs when they occur adjacent. And that's actually a bit dangerous if you're adding potentially unsafe postulates so that REFL proofs suddenly become possibly unsound. There are more examples. I've done PCF with quite a bit of checking, and I'm currently doing scheme, and you can find those online. You find the link in the paper. And I think to make this safer, what I would suggest, and what's also been, I think, confirmed in helpful discussions I've had with people here, so rather than cheating on and putting in these unsafe postulates, we really need to look seriously at what postulates are needed for synthetic domain theory in Agda, using plain Agda, also including predomains as well as domains with closure under all the usual constructs. And assuming only properties that are going to be safe and consistent, we're going to need to assume some properties. All functions should be functions implicitly continuous, following Scott's original idea of synthetic domain theory, and allowing unrestricted recursive domain definitions, where we hopefully can get somebody to extend the Agda type checker to deal with those. So thank you. That's my presentation.
Questions?
Relay.
Yeah, thanks. So I was kind of wondering what the limits of this approach were. So in particular, are you
speaking to the microphone?
Oh, sorry. So I was sort of wondering what the limits of like using the postulates and trying to get everything to go through this way were. In particular, for example, can you write down the fixed point combinator and show that it's a fixed point, or will that need more information about how this isomorphism functions?
For the PCF semantics, there is a fixed point operator that's added together with an unfolding. And in order to check PCF terms that have fixed points in them, one shouldn't unfold the fixed point unconditionally as a rewrite rule, because that would then just give non-termination everywhere. But if you put in a derived rewrite rule, which only unfolds it when it's applied to something else, then that seems to, well, it worked for PCF, that I could then terminate just using that rewrite rule for terms that had fixed points in them. So we can deal with fixed points. We can potentially add notation for limits. You don't actually need to express least upper bounds when you're writing down a denotational semantics, so long as you have the fixed point operator built in. And Strachey's idea was always that when he was using, before Scott domains came along, Strachey was using lambda notation with the intuition that the paradoxical combinator Y did correspond to unfolding computations, and basically that's what one can still do.
Okay, thank you.
Hi, what were your main difficulties when using Agda for this work?
My main difficulties, well, first of all, I only started using Agda last year, so it's been a learning curve, should we say. Luckily, I have people in Delft, where I am now, who have been very helpful, and otherwise I might not have got very far. I should mention that the one I did for the inheritance semantics last year is relatively clumsy, and I should go back and revisit that and try to do it better. It was trying to be more of a compromise between the type topology library and the lightweight approach. I hadn't really made it lightweight enough at the time.
So a basic question about synthetic domain theory. So you work in the internal language where every function is continuous, but then don't you want to don't you need some modality or something to distinguish the Scott domains from ordinary sets?
Yes,
for example, like the set of terms, but you use the same function simple for the continuous function between the Scott domain semantic and set of terms. I'm
currently trying to digest Alex Simpson's paper from 2004, 20 years ago, where he has a very comprehensive framework that includes both predomains, which include sets as a special case, and without any ordering, or just a discrete order. But yes, he has a notion of partial maps and lifting functor, and he relates partiality to lifting, so it seems that he doesn't need any extra modality, but he even supports recursive domain equations because he proves algebraic compactness for his underlying model. But I'm not fully on top of that paper yet, so I can't say more.
But there seems to be no issue to directly.
Not as far as I know, but don't quote me on that. Oops.
Last question.
So before you mentioned synthetic domain theory, what I thought of as a way to make things nicer in a simple way would be to redefine application and not the abstraction. To get the appropriate continuity witnesses to go around. Have you tried that?
So you mean building on top of the type topology library?
Yes. Yeah.
So then you still have the obligation of proving things continuous. You need to have in a sense, you need to have a meta theorem that will guarantee that for your application and abstraction are always preserving continuity. And then then you might. I haven't tried that because I don't know how to do meta programming and meta theorems in Agda.
No, but even without meta programming, I think you could keep the approach with a pair, but then define lambda to act on these pairs and application to act on these pairs with a type that says that if they are continuous in the appropriate sense, then you get what you want.
I think that going back to the long way back.
So in your example, you need something by substitution, so it's not.
So one can sweep it under the carpet in a sense, and stop it intruding too much on the actual semantic equations, but the problem is still there. I don't think you get rid of the problem. Okay, thank you.